Hi, this is Ramji Sharma. In this video, we'll be looking at the higher order partial derivatives, especially the second order partial derivatives of a function of two or more variables. Our first example says for the function f of x comma y equals 5x squared plus 4x to the 6 y squared plus 3y to the 4, find the value of f sub xx to negative 2. So the notation here, f sub xx is the partial derivative of f with respect to x, and then the partial derivative of the result obtained in the previous step with respect to x again. So we're differentiating this function with respect to x two times. You can, if you had a single variable function, this would be simply the second derivative of this function. Since this function is a function of two variables, x and y, we are going to differentiate this with respect to x two times by keeping the y variable fixed, which means the y variable will be considered as a constant. To proceed this, we're going to start with inside, and then we move to the right side or the outside. Or you can think of moving from left to right. And of course, you have these numbers to plug in, but before we can plug these numbers in, we have to find these two things. First of all, we'll have to find f sub x, x comma y, as our first partial derivative, and then we'll find the second partial derivative, which is f sub xx, x comma y, and then eventually we'll replace the first variable by the number in the first position and the second variable by the number at the second position. Alright, so let's start with f sub x, x comma y. Now I'm going to keep x comma y as an explicit expression because eventually I'm going to have to replace x and y by their values. Well, in this case, we're differentiating this function with respect to x, which means the variable y will stay constant. The first term, 5x to the 2, will become 5 times 2, which is a 10, and x to the power 2 minus 1, which is x to the power 1, which means x, using the power rule, plus the second term is a mixed term containing x and y. As I mentioned earlier, the y variable is going to be fixed, so all we have to do is just differentiate the x variable, and in this case x has the power 6, so we can apply the power rule, which means it's going to be 6 times 4, which is a 24, x to the power 6 minus 1, which is a 5, and y will stay back. So there is no change in y variable at this time. And the last term is a purely y dependent variable, meaning there is no x variable involved in it. So the derivative of this entire term with respect to x is going to be 0. Okay, and that 0 is really going to disappear. Now we're going to have to find the second derivative, in this case the second partial derivative. So the second variable for differentiation is still x, so we're going to differentiate this result with respect to x again. That's why we're going to write this as f sub x is our initial notation, and we're going to add the second variable that we're differentiating with, and that's again x, and we're going to write x comma y, and that's now going to be the derivative of the first term, which is 10x, and we're differentiating with respect to x. So the derivative of x with respect to x is 1. That means it's just 10. Plus, the second term is a mixture of x and y, and the term, the y variable is not going to change. It's going to act as a coefficient. So we have 24x to the 5 y squared. You can, I should have mentioned it earlier, but anyway, let me do this now. So in the second line here, 24 x to the 5 y squared. So the coefficient 24 of course is a number, and y squared is also going to behave as a coefficient, so it's going to be 24 and then y squared is one single coefficient, and then x to the 5. So as you know, when you differentiate a power of x with some coefficient in front, that coefficient is not going to change, so it's just going to be 5x to the 4, and that 5 will multiply the 24, so it's going to be 120, because 5 times 24 is 120, I hope. And then you subtract 1 from 5, that's why x will have the power of 4. And I want to still keep the y after x, so it's going to be y squared. And then the 0 is going to disappear, so there's nothing to do here. Okay, finally, we'll have to replace x and y with their values. So this notation, the subscript notation xx, is going to stay back, but the arguments are going to change into 2 and -2, and that's going to be 10, which is independent of x and y, so it'll stay back, plus 120, and then x is going to become 2, and remember, whenever you are substituting, it's a good practice to put that quantity inside the parenthesis, and then power 4, and y is a -2, and again the power is 2. So I'm going to separate these things from the main answer here, and it's going to be I think we need a calculator to calculate this thing, so let me bring my calculator up here. So we have this 10, so you don't see all of the calculator, but just this portion here in the recording, and that's okay. 10 plus 120 times, so here we have a parenthesis 2 and then 4. That parenthesis for this calculator is really not necessary, but I'm gonna put that parenthesis anyway, because that's not gonna do anything different. So that's 2 to the 4, and then move this cursor down, and then again that multiplication sign is not really necessary because the parentheses themselves are the multiplications, but just to be on a safe side, I put that parenthesis, the multiplication sign, and the parenthesis open. Now this minus right here is the negative. There are 2 minuses in this calculator, as you can. Okay, unfortunately, I cannot move this calculator anywhere. Here, right here. So this negative. So there are 2 negatives, as you can see. So we're going to use that second negative, I mean the one at the very bottom with the negative inside the parentheses. So I'm going to use that one. So so the negative, so again I'm going to take a little longer than what you would expect me to do here, but it's worth it because you need to know all of these steps so that your calculation is not messed up. So, and of course when you are doing it in the real life situation, you're definitely going to do it faster than this, but I'm just doing it for the purpose of teaching, so I may go a little bit slower. So so I have this, and if I enter everything correctly, I am supposed to get the right answer. So let's see. And sometimes if you don't enter these numbers correctly, and if there are some syntactical errors, then the calculator will give you some weird message, and that could be a very frustrating situation, especially when it comes to taking the test. Okay, I hope I entered everything correctly, and the answer here is 7,690, which is a rather big number, and that's okay. So 7,690. So let's copy that here. So it's going to be 7,690. That's our answer. Next example. In this example, we have this function f of x, y, equals 2x to the 4 plus 3x to the 6 and y to the 4 plus 5y to the 4. And this time we're finding the derivative of f, I should say partial derivative of f with respect to y and then with respect to y. So the second order partial derivative of f with respect to y evaluated at the point 0, 1, meaning the value of x being 0 and the value of y being 1. Okay, so as before, this requires two steps. The first is f sub y, x comma y, and the second step after that is f sub y, x comma y. And of course, after you evaluated, after you find the derivative, you just plug these values of x and y into their positions. So it's going to be 0 there and then 1 there. Okay, so let's do the first partial derivative with respect to y, which is f sub y, x comma y, and that's going to be the derivative of this entire right hand side with respect to y. Now when we're doing it with respect to y, we're keeping the x variable fixed. So if there is a term containing numbers and only x, that entire term is considered as a constant, and the derivative of a constant is 0. So that first term turns into a 0, plus the second term is a mixture of x and y, so that x here is going to act as a coefficient. That's why we're going to keep that as it is and differentiate the y part, and these are all powers, so we're just going to use the power rule. So this 3 is going to stay back, x to the 6 is going to stay back, and y to the 4 becomes 4y to the 3. So that 4 multiplies 3, and that becomes a 12. And x to the 6, I'm just going to copy that, and y to the power 4 minus 1, which is a 3. Plus the final term is 5y to the 4, which is a purely y dependent term, and its derivative is just the ordinary derivative of y to the 4 with respect to y. So that's going to be 5 times 4, 20, y to the 4 minus 1, which is a 3, and that 0 is going to disappear. Now that's our first derivative. Now let's look at the second derivative, which is f sub y, y. So that second y is the thing that is coming after this y. So the position here matters. We always go from left to right. That's the direction we'll follow in these higher order partial derivatives. You may have more than 2 there in other courses, but for this course all we are doing is just the second derivative, so it's okay. And that's going to be x comma y. And so again we're differentiating this result from the previous line with respect to y. Anything that contains y is gonna follow the power rule or whatever rule we'll have to apply, and then any term containing other than y is going to disappear. So of course the 0 is going to disappear, and the 12x to the 6y cubed is not going to disappear because that contains y. So we're going to have to differentiate y cubed, keeping the other things as they are. Now y cubed, when differentiated, becomes 3y squared. That 3 in the front will multiply 12, so that's going to be a 36 x to the 6, and then y becomes 3 minus 1, which is a 2. Now don't differentiate x at this time. Do not put this as 6x to the 5, because we're doing it with respect to y. This is the one that is acting at this time. So earlier this one was acting on this derivative, and now this is the one that is acting. So if that arrow, that okay, let me remove this from here if I can at all. Maybe I can't. Oh, actually I did. So so you gotta know which subscript is active, or which subscript is acting on the right hand side. So this is the second one that is acting here. So that's affecting the power of y. So it's going to move the power out in front and then subtract 1 from that power. And then the second term is a 20y cubed. Now this, because it contains y, so we're going to have to differentiate it using the power rule. So it's going to be 20 times 3, which is a 60, and then y to the power 2. Okay, so we've gotten this far in our steps. So now we're gonna have to replace x and y by their respective values given in the question. So f sub y, 0 comma 1 equals 36 is gonna stay back, and x is 0 to the power 6, and y is 1 to the power 2, plus the second term is 60, and then 1 because y is 1 to the power 2. And this 0 right here is going to make the whole entire thing into 0, so that first term completely disappears. The second term is 60 times 1 squared. 1 to the power 2 is just 1, so it's a 60. You can try it in your calculator if you're not sure. Okay, one last example here. The third example says for the function f of x comma y equals 5x to the 4 plus 3x cubed y cubed plus 3y to the 5. Find the value of the second order partial derivative f sub yx 1 comma negative 1. And there is an extra term here which I'm going to leave as an exercise for you later. So I'm just going to work on this one. Now remember, we're going to move from left to right. So we're going to differentiate this with respect to y, and then we're going to differentiate with respect to x. So the steps are to find the derivative, I should say the partial derivative of this function f with respect to y, x comma y. And then the second step is going to be the derivative of that result from the first step, which is f sub y, with respect to x, and then we're going to do x comma y. So that's how we'll find the derivatives, and then eventually we're going to replace x with 1 and y with negative 1. Alright, so let's move on and try this out. So the first one is going to be f sub y x comma y. So this time we're going to differentiate the right hand side with respect to y. In that case, anything that contains only x and number is going to disappear because that's a constant. So this first term is just a pure number for y because there is no y involved there, so it's going to be a 0 plus the second term is a mixture of x and y. That's why we're going to keep the number and x part as it is, so that's going to be 3x cubed and then the derivative of y cubed. Now I'm going to move one step ahead and already multiply 3 which is going to move out in front, and that's going to affect that 3 that is already sitting there. So those 3 multiplied together will give us a 9, and then x cubed is going to stay back and y is going to lose 1 power, so it's going to be y to the power 3 minus 1, which is y to the 2 plus the last term is a purely y dependent term, so we're just going to differentiate it in a regular way. So it's going to be 5 times 3, which is a 15, and y is going to be 5 minus 1, which is a y to the 4. That's our first order partial derivative with respect to y. Now we're going to differentiate this result with respect to x, because that's the last step. So in the notation, we're going to copy f sub y from the previous line, and then we're going to add x right after y, and then the other structure x comma y will stay back. So again, if the notation is something you're worried about, I would say because these notations will appear the same way in many different examples, so the only way to be comfortable with these notations is to practice more examples like this. There is really nothing more than that. It's just a notation. So as long as you know how to solve the problem, the notation shouldn't bother you that much. I mean, it's just a name, just as you know, my name is Ramji. If you hear it for the first time, it might bother you, but if you hear it a lot, it shouldn't bother you. Same way with this notation here. Of course, if you want to change my name, that's gonna be a disaster, right? So you can't change this notation here. So here we're gonna differentiate this result from the first step with respect to the second variable. I mean, second variable, I should be careful when I say the second variable. What I really mean is the variable x, the variable in the second position, which is x. Usually by second variable you may mean the y variable, but here that's not what I mean. So the variable in the second position, which is this variable, the x, that's going to be active on this right hand side. So we're differentiating with respect to x. So in that case, all the y's will behave as a constant. So 9 and y squared, I'm thinking about the first term, so 9 and y squared will stay back, and then x cubed will undergo differentiation. So the derivative of x cubed is going to be 3x squared. That 3 multiplies 9, and that's going to make it into 27, and then x to the power 2, because x is going to lose power 1 power from there, and then y will stay back as it is, so that's going to be that. And then the 15y to the 4 is a purely y dependent term, and we're doing it with respect to x. So that whole thing, 15y to the 4, is a constant. That's why its derivative with respect to x is 0. So you have to pay attention to the variable you are differentiating with. Sometimes one variable stays back, sometimes that same variable becomes a 0, depending on whether it's a coefficient or it's an independent term. Um, and that's the second order partial derivative of this function. And now finally we'll replace x and y with 1 and negative 1. So in the notation side, we're going to write f sub yx. So these two yx will stay back, and then the arguments x and y will be replaced with 1 and negative 1. So that's how the notation is written. So you can't change this part. On the right hand side, you have 27, and now we're going to replace x by 1. So that's going to be 1 to the 2 and a negative 1 to the power 2 again. Now 1 to the any power is 1, but the negative 1 is going to become 1 or negative 1 depending on the power. If the power is odd, that negative will stay negative. If the power is even, then the negative will become a positive. In this case, negative 1 to the 2 is a positive 1. So these two are basically 1 times 1, so they're not going to change anything. So it's 27. Again, you can use a calculator and check this answer if you are not comfortable here. Okay, now as an exercise, you might want to go ahead and do the second part of this problem, which is f sub xy 1 comma negative 1. Now remember the order in which you are going to take the partial derivatives and then eventually replace x and y with a 1 and negative 1. And the answer is supposed to be the same. That's how you will check your answer. So you'll get the same 27. If you don't get 27, that means your process is somewhere. There's something that you should check. All right. So I hope you enjoyed watching these the solutions of these three problems in this video. I hope I made a few things clear here, but again, remember, this is not a detailed lecture on the partial derivatives. Just a review of a few important concepts. All right, thank you for watching, and I'll see you in the next video. Bye for now.